In this tutorial, we're going to be talking about the ionization energy. As the name specify, ionization energy is going to be the energy required to remove an electron from a gaseous atom. So for example, if I have a metal and the metal in its gaseous form, when it goes on to lose an electron, so it's going to make M1 plus 1 electron. So it's going to be requiring an energy. So I would say ionization energy, which is going to be similar to writing in a delta H here, is going to be some positive value because it's the energy required, which tells you it's going to be an endothermic reaction, because any processes that requires energy to take place is going to be an endothermic process. And think about this. If you have an element just sitting on the table, it's just not going to lose an electron on its own. You must do something to make sure it loses an electron. And typically you have to provide it enough energy, so-called ionization energy, so that it can lose one of its electrons. Now, the question is, when will it be easier to remove an electron? So think of this. You have a bigger element. All right, so let's take compare of this element right there and this element right there. So I got element A and I got element B, and we got an electron that we're looking at, focusing on an element A, and electron on element B that we're focusing on. And think of this, in this particular case, we have obviously nucleus at the center of the atom. Now, which electron is going to be easier to remove? Is it going to be electron in element A, or is it going to be electron in element B? Well, if there isn't a stronger attractive force toward the nucleus, it's going to be harder to remove an electron. So another way of saying, if the nucleus is pulling onto that electron, it's going to require more energy to remove an electron. Okay, and if it requires more energy, we will just call it, we need higher ionization energy. So if it's further away from the nucleus, it's going to have a weaker attractive pull, like in case of A. And if it has a weaker attractive pull, you will need lower ionization energy, and you can also call it, it's going to be easier to remove an electron. So in case of A, it's going to be easier to remove an electron than in case of B. So another way of saying, it's going to have low ionization energy, and the electron in atom B will require high ionization energy. Okay, so what happens as you go move along the period? So when you go move along the period from left to right, we know your Z effective increases, which means the attractive force from between the valence electrons and the nucleus is increasing, and that also decreases the size. So it's not far away from the nucleus, and if it's not far away from the nucleus, it's going to be harder to remove an electron. And if it's harder to remove an electron, you will need higher ionization energy. And when we're looking at just the trend in the main group elements, your ionization energy is actually going to be increasing when you're going from left to right in a period. Okay, well, on the other hand, when you're looking at down the group, your size decreases. Or, sorry, your size increases rather. Z effective is not that prominent when you're going down the group. It's just the size. Size increases because you're adding different shells as you're going down, which means you are going away, your valence electrons going away from the nucleus, and that's going to have a weaker attractive pull. So if your size is increasing when you're going down the group, your ionization energy is going to be decreasing. So you need low ionization energy to remove an electron when you're going down the group. If I want to compare the ionization energies between the metals and the nonmetals, metals usually have low ionization energies. Because think about this, when we talked about ionic compounds and we were making anions and cations, what we learned that metals like to lose electrons. Now, one of the reasons why they like to lose electrons because they have low ionization energies than the nonmetals. So if you're generally comparing a metal with a nonmetal, you would have low ionization energy for the metal, and the nonmetal would have high ionization energy. Let's talk about maybe some of the exceptions, and some of the exceptions we have. One of the exceptions we have is in group 5 and 6 element, actually. So when we're looking at, let me change the color here, we're looking at the group 5A and group 6A. So when I'm going from, assume I'm moving along from nitrogen to the oxygen, you would expect nitrogen would have low ionization energy and oxygen would have high ionization energy. All right, so that's going to be your expected. However, that's really not the case, and the reason why that really happens, when we're looking at electronic configuration of nitrogen, it's going to be helium 2s2 and 2p3. And in case of oxygen, it's going to be helium 2s2, 2p4. Okay, so when I'm writing down the symbol, the atomic orbitals there, and if I just focus on the 2p here, so remember 2p has 3 orbitals in there. So in that case, we have half-filled every single orbital. But when I'm looking at the 2p4 for the oxygen, we still have 3 orbitals, but then they are not fully half-filled. Okay, you got this extra electron there that can be easily removed as compared to removing an electron from this fully half-filled 2p subshell in case of nitrogen, because this particular arrangement that we already have in case of nitrogen is going to be more stable. It's going to be harder to remove an electron. So that's why, even though we expect that nitrogen would have low ionization energy than the oxygen, technically nitrogen have higher ionization energy than the oxygen. So nitrogen ionization energy is higher, greater than the ionization energy for the oxygen. So make sure you remember this exception here, and that's obviously gonna follow along the group. If I'm comparing the ionization energy between the phosphorus and the phosphorus and the sulfur, your ionization energy for the phosphorus is going to be greater than the ionization energy for the sulfur, and the reason is going to be the same because of the fully half-filled atomic orbitals in case of group 5 elements are more stable and they are less likely to lose an electron. Okay, let's take a couple of examples here. So suppose I got this nitrogen, neon, and lithium. All right, so seems like they are going to be in the same. They are in the same period in here. So we have lithium right there, we got neon right there, and we got nitrogen right there. So if they are in the same period, what we know, as we move from left to right, your ionization energy increases. So that means lithium is going to have the lowest ionization energy, followed by nitrogen, and then after that neon is going to have the highest ionization energy. Usually noble gases have high ionization energy because they already have stable electronic configuration and they don't want to really lose an electron in that particular case. But just remember this particular exception of group 5 and group 6A. Okay, let's take another example here. we have, let me change the color here, we have helium, we got carbon, we got francium, and we got nitrogen there. So it seems like they are in actually different periods and different groups, so we really don't have a very straightforward trend here. So helium is going to be right there, francium is all the way down here, carbon is in the second period right there, and the nitrogen is right there. Okay, so think about this. We know the metals have low ionization energies than the non-metals, so the only metal we have in this particular set is going to be francium. Okay, and you can also think of this way: as you go down the group, your ionization energy decreases, and francium is all the way down in this particular set. Even though they are not in the same group, but you can clearly see it's further down in the periodic table. So francium, being the metal and furthest down in the periodic table, is going to have the lowest ionization energy. Okay, now helium is all the way onto the top in the periodic table. It's in a noble gas, so it's going to have a very high ionization energy. So helium, I'm going to put that at the very end. Now, between carbon and nitrogen, since they are both in the same period, and as we know, as we move to the right, ionization energy increases. Nitrogen is going to have higher ionization energy than the carbon. Okay, and obviously keep in mind you always want to be on the lookout for the exceptions in there, but this doesn't have any of the exceptions in there, so we just follow a regular trend in there. Okay, so this is how you're going to be looking at your ionization energy. So let's look at successive ionization energy. So what that really means, if I lose one electron going from magnesium gas to make magnesium 1 plus and 1 electron there, and that's going to be called an IE1, ionization energy 1, and then to lose the second electrons from Mg1 plus gaseous. So when it's losing the second electron, it's going to make Mg2 plus gaseous here, plus 1 electron here. This particular one is going to be called an IE2. So that's what the successive ionization energy is, which means after losing the first electron, what happens to the next ionization energy? And if you already have a positive charge, which means your Mg1 plus is going to be smaller than the Mg, and you're going to have a stronger attractive pull coming from the nucleus onto those remaining valence electrons. And if that's the case, it's going to be harder to remove the second electron. And your successive ionization energy is always going to be bigger than your previous ionization energy. So I can clearly say here, your IE2 is actually going to be bigger than IE1. Another way of saying, it becomes harder to remove a second electron after you have lost the first one. Okay, well, in this particular case, I do want to compare the third ionization energy as well. So if I have Mg2 plus, and it goes on to make Mg3 plus gas, everything is in gas phase here, plus an electron. So this particular one is going to be called an IE3. Now remember, magnesium actually has 2 valence electrons. And when we learned about making ionic compounds, we did learn that magnesium wants to lose 2 electrons so that it gets to unstable electronic configurations. Now, once it has lost second electron, it actually will not lose the third electron. And the reason why it will not lose the third electron, because this has a stable electronic configuration as that of neon, because it's got 10 electrons. So when we're comparing the ionization energy 3 with the 2 and 1, it's actually going to be even bigger. So ionization energy 3 is going to be much, much bigger than ionization energy 2. And obviously ionization energy 2 is bigger than ionization energy 1. So sometimes, based on how big the jump is between the ionization energies, you can predict the number of valence electrons. Okay, well, let's look at an example here. Suppose I have this hypothetical element that has the successive ionization energies given, and we need to figure out how many valence electrons you're going to have in there. So the first ionization energy is 550 kilojoules. The second one is 1500 kilojoules per mole. Makes sense because as you're moving along, your ionization energies should increase. IE3 turns out to be 2900, and when we're looking at IE4 is 15,000. Well, there is an unusual jump in the ionization energies. Yes, it's supposed to increase, but that's a very big jump going from 2900 to 3000. What that really means, after losing 3 electrons, it does not want to lose any more after 3. So that means that's going to be your valence electrons. So it has 3 valence electrons, and once it has lost those 3 electrons, it will not, or it does not want to lose the 4th electron because it has gotten into the stable electronic configuration. So that's how you're going to be predicting the number of valence electrons in that particular example. Alright, so hopefully this was helpful. If you guys have any questions regarding the ionization energies or any other particular questions on the ionization energies trend, feel free to leave any comments in the section below.